Hey, so here's another LeetCode problem. It's an easy one. 346 moving average from data stream. I have tried this before one time, apparently, about some time ago. So hopefully I can solve this now without looking at the solution. So we're given a stream of integers and a window size. Calculate the moving average of all integers in the sliding window. That giveaway for the technique that we're going to use. Implement moving average class. Moving average int size initializes the object with the size of the window. Double next int returns the moving average of the last size value of the stream. Okay. Is there nothing that inserts values in it? What? Okay. But what is in the window? How do we get the values? Moving average. Given a stream, blah, blah, calculate the moving average of all integers in sliding will implement moving average class. Moving average in size initialize the object with the size of the window size. Double next returns the moving average of the last size values of the stream, but where do they come from? I don't know. A mystery. Okay, so the size is at least going to be 1, whereas between minus blah blah and plus blah blah. And most 10 to the 4 cells will be made, calls will be made to next. Oh, I see. So we get the values here. I'm blind, sorry. And that means we're going to add this to our window and we return the average, which is okay, nice. So I think there's an easy way of how we can solve this. We just need a first in, first out data structure that allows us to add and remove elements from the head and the tail in constant time. And we need to keep track of the sum of all the elements in our little window and how many there are. Well, we know because size defines that. But in the beginning, we might have less than size elements in it. So we do need to be able to compute the size of our little FIFO. And then what we'll just return is the sum divided by whatever the size is. So that's what we're going to do. And in this example, let's just check if what I just suggested will work. The moving average size is 3. We add a 10, a 1. So, well, one number, the average of one number is that number. Now we add 10, so the average of 11, 1 plus 7 is 5.5. Then we add 3, so it's 14. What is 14 divided by 3? It's 4.6666. It's 6666666. And then we add the 5, and then suddenly we have the average of 19? No, 18. Right? 10, 15, 16, 17, 18, 19. Well, yeah, because the window size is smaller, right? It's only size 3. So that's why the 1 pops out of the window. So now the average of 3 elements is 6. All right, cool. Let's do this. So we say self dot capacity. What size, capacity is the upper limit of the size, and the size is the current size. That's how I would define that. I would actually change it. Capacity equals capacity. And yeah, self.window equals, well, we're going to use the deck from collections. That's what we're going to do. And as a convenient helper. And what we're also going to do is we're going to have self.window sum equals 0. So we'll keep track of all the elements that are in here. So what do we do? Well, the first step is we say self.window append the value. Self.window sum add the value. If self.window length is beyond our capacity limit, what do? Well, we need to pop out the leftmost element from our little deck, right? Self.capacity, right? If that is the case, we will do self.window sum minus equals self.window dot top left. That's what we'll do. And yeah, we also need to keep track of the size of the deck. Well, we already have that. It's encoded in the deck itself. So yeah, we return self.window sum divided by the length of self.window. That's how that works. So yeah, so this is an O of 1 method call. This is an O of 1 method call. Every operation is constant time, but we'll need capacity space for this. Let's test it. So test case works. Let's submit this. And it also works. Fantastic. So yeah, so that's how you solve that. O of capacity space and O of 1 time.